In the last video, we talked about the process for creating number systems. And in this video, we're going to go ahead and do the first step of that, and that is to develop an intuitive understanding of what real numbers are. So we're going to develop two concrete models of real numbers to help us understand them better. And then we're going to use these models to see if there are any numbers that are not rational. Because if we go to all this trouble trying to construct the real numbers, and it turns out that they're the same as the rational numbers we already had, this is a big waste of time. So here are two ways of thinking of what the set of real numbers is. The first I call the displacement model, and here we're thinking of a real number as a displacement of an object. And what I mean by displacement here, it's kind of like distance, except it takes direction into consideration. There are two directions, forward and backward. Forward indicates positive displacement, backward gives us negative displacement, so that gives us the positive real numbers and the negative real numbers. The next model is one that you're probably super familiar with. That is the number line model. Here, a real number is a point on a horizontal line. And before we can start identifying real numbers, we have to put the additive identity somewhere on the line. This is sort of like the starting point if we're thinking about our displacement model. But we need to put that somewhere on the line so that we can have a dividing point between negative numbers and real numbers. And since a line is infinite in both directions, it doesn't matter where we put it. So points to the left of 0 are the negative real numbers, points to the right are the positive numbers, and the actual real numbers are determined by how far away they are from 0 and what side of 0 that they're on. So this is kind of nice because all rational numbers represent displacements, which means that the real numbers contain all rational numbers. The next question then is, are there any numbers that are not rational? And how would we determine that? Well, let's start with some distances or displacements that we already know. We know the number 1 is a real number, so we can draw line segments of length 1. And the way I'm going to draw them is so that they're at right angles to one another. And then we can connect the ends of those two line segments to make a triangle, right triangle. And it has some distance c. Now, that is a distance of a line. That's a displacement. That's a real number. So c is a distance, which makes it a real number. The question is c rational? Well, we know how Pythagorean theorem works. Gives us c equals square root of 2, c squared equals 1 squared plus 1 squared, right? So really the question that we're asking is square root of 2 a rational number? We already know that it's a real number. Is it rational? Well, it turns out it's not, and this is something that you've probably seen before, but I'm going to go ahead and prove this to you anyway. We're going to use proof by contradiction, which means we're going to assume that the square root of 2 is rational, and then prove a contradiction from that. So if square root of 2 is rational, that means we can write the square root of 2 as the fraction of two integers, a over b, where the denominator b is non-zero. And we can assume the fraction is in lowest terms. That's perfectly legitimate. And it turns out that's going to be helpful in figuring out our contradiction. And what I mean by lowest terms is that a and b don't share any common factors except for 1, or if you like negative numbers, negative 1 as well, but no others. So we have square root of 2 equals a over b. Square roots are inconvenient, so we're going to square both sides of that equation. Fractions are also inconvenient, so we're going to multiply both sides of that equation by b squared. And then we notice that since b squared is an integer, 2 times b squared is an even integer. That means that a squared is an even integer. And since squaring odd numbers gives us odd numbers, probably something that you proved back in Math 210, that means that a has to be even. Can't be odd, because if we squared it, we wouldn't get an even number. But even number means that a is equal to 2 times k, where k is an integer. And now we can put that in for a in our last equation. We have a squared equals 2 times b squared. Put in 2k for a. We get 2k quantity squared equals 2b squared. We can square that out. We can divide out a 2. And now we can see that b squared is an even number since it is 2 times an integer. And now we can play the same game with b as we played with a. Since b squared is even, that means b is even. But since a and b are both even, that means they have a common factor of 2, which means that the fraction was not in lowest terms. That is a contradiction, which means that the square root of 2, it's a real number, but it is not rational. And that's a comfort because now we know that the rational numbers and the real numbers cannot be the same number system. So we're going to work on some more of these in the in-class activities, but I want to give you a theorem that's going to actually be really helpful when we do that. It sort of corresponds to what we did with the odd and even numbers in the proof for square root of 2. And you may have seen it before back in modern algebra, Math 350. It's called Euclid's lemma. And it says that if you have a prime number p and you have a bunch of integers where p divides evenly into the product of those integers, then p has to divide evenly into one of those factors for at least one of the AIs. All right, so one of the things we're going to explore in the course is how common irrational numbers are. We just found one of them, but it turns out there are a ton of irrational numbers. In some sense, in a sense that we will define later, there are more rational numbers than there are, or more irrational numbers than there are rational numbers. And we're going to see how that works in section 2.3. I don't want to get too weighed down in this video. But now you're ready for the in-class activities. It's called Irrational Numbers, and if you look at the link right below this video, that little triangle, click on that sucker, and that will get you to those in-class activities.